Hello, and welcome to today's lecture on decision trees. Right, so what is a decision tree? A decision tree is basically a flow-like structure which will consist of nodes and branches, right? So where each node represent an attribute and each leaf node represent a classification rule, right? So these are branches, right? These are nodes, and these are leaf nodes, right? So your leaf nodes basically assign a classification, right? Your branches represent attribute value, right? And this is nothing but a feature of an instance or a data set, right? So the internal nodes that you have here, these internal nodes represent or test an attribute. So if you consider, in general, a decision tree is disjunction of conjunctions of constraints on attribute value of instances, basically. So it is basically a disjunction of conjunctions, right? So what do I mean by that? We'll see that by an example. So conjunction is basically and disjunction is basically or. All right. So when I say disjunction of conjunction, let's take an example and let's try and build a decision tree out of logic. All right. So let's say we have an example A conjunction not of B, right? So how do you build a decision tree for a logic like this? So I would say start off with building a table. Let's say we want to build a table, a truth value table for the following logic, right? So this would be 1 0 1 0. Therefore, if you take A and not of B, what you'll get is 0 0 1 0, right? Now you have a decision tree. You can build a decision tree out of these logic values, right? How do you do that? Let's say you start off with A, right? So A has two values, true or false, where 1 represents true and 0 represents false, right? Now if you see, whenever A is false, right, our output is false, right? Or you can see that whenever A is 0, the result does not depend on the value of B or not of B at all. Therefore, we can directly write if A is false or A is 0, the result is always going to be 0 or false. Now, if you take A as true value, right? If you take A as true value, you have 0 and 1 associated with it, right? Because you have two different outputs for A equals to 2. Therefore, we need to take in consideration B as well, right? So B has two values, true and false. Now see, when A is true and B is true, A is true and B is true. So your output is false. Therefore, you write false. And when your A is true, B is false, your answer is. Therefore, you get your decision tree. All right. Let's take another example. Let's take A XOR B. Right. If you take A XOR B, you build a decision table for A XOR B. Right. You get 0 0 0 1 1 0 and 1 1. Right. When you take XOR of A and B, this would be 0, 1, 1, 0, the decision table for it. Now if you go on about building a decision tree, right? So when A is false, the answer depends on value of B as well. And when A is true, the value depends on value of B as well. So therefore we need to take B in both the cases. Now B has two values for its attribute, true, false, right? So now when A is true, B is true, answer is false. A is true, B is false, answer is true. A is false, B is true, answer is true. This is false. Therefore you get your decision tree. Now you can also do it with B, starting off with B, right? You'll get a different decision tree. So there are different decision trees possible for one logic or for one data set. So that means there are multiple types of decision trees possible, and that all depends on the data and the attributes that you have. Now comes the main question of how do you select your attribute?
Yeah. So now we tackle the question of how do we select the right attribute and how do we choose which attribute do we have to split on, right? So attribute selection. So there are many ways of selecting an attribute, right? So number one way would be entropy, right? Which is defined as E of S, which basically tells you variation in the data. What do you mean by variation in data? Okay, let's say if we have high entropy for a data set S, right? High entropy would mean, or let's take X for an attribute X. High entropy would mean that X is boring and uniform. What do we mean by boring? That means it does not give out too much of information, right? Whereas low entropy means X is interesting and varied. So you could say that entropy is basically inverse of the information that data holds, right? Now, how do you define an entropy? And entropy is defined as uh, h of x is equals to minus sigma pj log to p of j, where j goes from 1 to m, right? This defines the entropy of attribute x. I'll explain this formula as we proceed. So where P of J is the probability of occurrence of J type of in an attribute X. Let's say X is made up of four types of, let's say, rainy, windy, sunny, and let's say cold, right? Rainy, windy, sunny, and cold. So these are basically four types of features of a single particular feature X, right? So this would mean in order to calculate the entropy of X, what you need to do is minus probability of rain log of probability of rain minus probability of wind log of probability of wind minus probability of sun log of probability of sun. So this is how you calculate, and so on, the entropy for particular X. That means it will tell you that when you split X on these four values, how much information do we gain or lose, right? If we have high H or high entropy, that means this data set was divided into uniform parts. So okay, in order to better understand it, let's take a two-class classification. All right. Now, if we consider two-class distribution, right, where capital S stands for sample of training examples. Now, if I want to draw an entropy versus the distribution of the data graph, what I'll get is something like this, right? So this is 0.5. This is not drawn to scale actually. Something of this sort. So this is 1.0. This would be 1, where this is equals to h of s entropy, right? And this is the distribution of the data set. That means if I remove this, okay, so that point would be somewhere here, right? So this basically means the proportion of training example in S. That means if let's say a data set S has two types, positive samples and negative samples, right? And let's say S consists of 40 total training examples, out of which 20 are positive and 20 are negative, right? So if you split on this, you won't get too much of information, right? If you split here, see what you're getting is you have equal amount of both types of training set, that is X, your set is uniform, right? And your entropy is the highest possible, right? When the data set is uniformly distributed, that is like 20 of one sort, 20 of another kind, you have the highest entropy, that is equals to 1. So for two class where we have positive and negative samples, entropy S would be defined as P positive log 2 of P positive minus P negative log 2 of P negative, right? Now, so as I was saying, for two class classification, we have this following formula derived from the entropy formula. Now, as I said, our S dataset is made up of 40 samples, out of which 20 are positive and 20 are negative, right? In order to calculate the entropy for this set, what we do is probability of positive samples is 20 by 40 log 2 of 20 by 40 minus negative samples is 20 by 40 log 2 of 20 by 40. What do you get out of this? You get minus 1 by 2 log 2 of 1 by 2 plus log 2 of 1 by 2, right? From which you get minus 1 by 2 minus 1 minus 1, right? Which is equals to 1, right? So you see, when the data set is equally divided, we have a very high entropy. And when data set is not so uniformly divided, we would have a very low. Now, what do I mean by that? Let's see, if S is made up of 40 samples, out of which 40 are positive and 0 are negative. So applying this and using this formula, we get minus 40 by 40 multiplied by log 2 of 40 by 40, that is 1. Now log of 1 is 0. That means whole entropy of S now becomes 0, right? Which means our X is varied, right? When the split occurs, we'll get a varied X, which will contain a lot of information. So our entropy of S basically measures impurity, right? basically measures impurity. Now, on just the basis of the impurity, we won't be able to select the right attribute that we need for splitting, right? For that, we introduce the concept of gain, 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 on a training set S with attribute A, right? Now, gain is basically your expected reduction in entropy due to sorting on A or splitting on A. Expected reduction in entropy due to splitting on A. Now, gain S of A is defined as entropy of our training set, right? Subtracted by summation of the split set, and this would be entropy of SV, right? What do I mean by this? Where basically your S is the set of examples that we want to split. Mode of SV is subset of examples where um, X is equals to V, right? Where basically V belongs to values in attribute A, right? So that means the attribute is equals to V and the entropy of that, right? Now, like I'll explain this with the help of an example so that it's more clearer to you. Because we want to find an attribute that maximizes a gain, right? In order to do that, let's take this example. This example was given in the slides. I'll explain it. So let's say you have two attributes, A1 and A2, right? You have a data set made up of 29 positive samples and 35 negative samples, right? And you have two attributes, A1 and A2, right? When you split on A1, you get a different decision graph or a decision tree, and when you split on A2, you get a different decision tree, right? So in order to know which attribute is better for splitting, we use the concept of information gain, right? Now, if we split on A1, we get two subsets. When A1 is true, you get 21 positive samples and 25 negative samples. And whereas when A1 is false, you get 8 positive and 30 negative samples. And when you split on A2, right? When you split on A2, you get 18 positive and 33 negative samples, while 11 positive and 2 negative samples. Now you want to know which graph should we proceed with? Should we go with A1 or should we go with A2? In order to find the right attribute for your choice, what you need to do is you need to find gain. Okay. In order to find gain, let's start with A1. Right. Let's start with finding the entropy for A1. Basically, entropy would be same for A1 and entropy of A2. Why? Because initial data set remains the same while splitting on the first attribute, right? It would be 29 positive and 35 negative samples for A1 and similarly for A2. So in order to calculate that, what you need to do is you need to use the formula of minus Pj log 2 Pj sigma. So if you take positive samples, total number of samples are 64. So if you want to calculate the entropy of A1, it would be minus 29 by 64 log 2 of 29 by 64 minus 35 by 64 log 2 of 35 by 64, which results in a value of 0.9936. Now this value h of s 0.9936 remains same for both A1 and A2. So now your splitting information depends on how your data set gets splitted on, right? Like you see the variation in the data set. Now once you've calculated the entropy, what we need to do is we need to find gain. Okay, in order to find gain, what we need to do is we need to, let's say for A1 we are finding, so entropy of set S minus the true samples upon total samples, entropy of true samples minus, and my bad, this is going to be plus um, false samples upon total samples, entropy of false samples. Okay, now this is going to be a big calculation. So we have calculated entropy of S, which comes out to be 0.9936. Now we calculate this part, the second part of the equation. In order to calculate the second part of the equation, we see we are doing for A1, right? A1 is splitting it into 21 positive, 5 negative, and 8 positive and 30 negative, right? For false and for true. So if we take the true side, mod of HT is 26, right? Upon total number of samples are 64. Now entropy of the true sample would become 21 by 26 log 2 of 21 by 26, right? Um, so this is subtraction. No, this is plus 26 by 64, 21 by 26 log, this is negative. So this would be minus 5 by 26 log 2 of 5 by 26, right? You've calculated the first entropy, multiplied it with mod of ST by mod of S. Okay. Now plus negative would be 38 by 64, right? Minus 8 upon 38 log 2 of 8 upon 38 minus 30 by 38 log 2 of 30 by 38. So if you calculate this value, this results in 0.99. You can use your calculators to sum it out, and what you'll be left with is 0.2869 plus 0.4408. This results in 0.2658. So now we have calculated gain for A1. Gain for A1 comes out to be 0.2658. Right. Similarly, if you go on to find the gain of A2, right, I'll write down the equation for you. So, okay, for A2, it was 18 positive samples and 33 negative samples. So 18 by 64 minus 18 divided by 18 plus 33 would be 51, right? Log 2 of 18 by 51 minus 33 by 51 log 2 of 33 by 51. So this calculates your first part plus 33 negative samples, right? Sorry, this wouldn't be 18, this would be 51, I'm sorry. And this would be 13 by 64 minus 11 by 13 log 2 of 11 by 13 minus 2 by 13 log 2 of 2 by 13. Now you subtract this value from 0.9936. What you will get as a result is 0.1643. So gain of A2 becomes 0.1643. Comparing both of these values, we see gain of A1 is greater than gain of A2. Therefore, we select A1 as the attribute to split on. So as you've seen, how we can select a particular attribute and start building our decision tree out of it. So now what happens is, for each particular data, there are many type of decision trees that are possible, right? Some of the decision trees do tend to overfit the data, or some decision trees do not capture all the information. So in order to find the perfect decision tree, we use the gain to find the attribute and keep on dividing it till we get our classification, right? Keep dividing um, on the attributes till you get all the classification rules covered. Okay, now what happens is sometimes our decision tree tends to overfit the data, right? What do I mean by overfitting? Like, it will give out some classification rules that are not even required by our data. So that slows down our computation and the processing process as well. So in order to overcome that, we introduce two techniques. Number first is pre-pruning, and number two is post pruning, right? So in pre-pruning, you basically at each step you check out if the tree is complete or not. If it is, you just remove all the next parts and you continue doing that. So you prune the tree before building the whole tree. While in post pruning, once you build out the whole decision tree, what you do is you start from bottom up and then you keep removing the nodes from it. So as you could see, pre pruning will always be faster than post pruning, but sometimes pre pruning leaves out some of the useful information that shouldn't have been removed, but it's still removed because it has not seen the whole data set yet. So basically in pre-pruning, stop growing the tree when the data split is not statistically significant, right? You're not getting much information gain out of it, so you stop splitting on it. And in post-pruning, grow the full tree, then remove subtrees which are overfitting your data. So it's pretty straightforward. So along with gain and entropy, we introduce two more concepts that are gain ratio and information gain, or split information, that also help you when your attributes have multiple values, right? Like in the past few examples, we have seen that there were just two types of values for a particular attribute. If there are multiple values for an attribute, and let's say those values are not your nominal or your category, they are categorical values, right? So what you do is you use gain ratio. So gain ratio is nothing, just an advanced version of gain, which is calculated as gain upon split information for s comma a. You just divide this gain with split information in order to capture extra information that we are missing out. Now what is split info? It's somewhat similar to what we wrote in the gain. So split info would be minus sigma. Instead of entropy, what we do is we do log, where v belongs to values of a. Okay. So it helps because it is sensitive to how broadly and uniformly attribute splits are instances. Okay. So these are two more topics. These are two more formulas that are like these. As you can see, you can directly use these to calculate the gain ratio for an attribute a, right? We've calculated gain. All you need to do is calculate the split information, divide the gain with split information to get the gain ratio on attribute. So now we have loaded ourselves with the information that we need to tackle the questions that are given in the tutorial PDF. All right, so if we start with the PDF, the first question is just expressiveness of decision trees, that I have taken up two examples that are A and not of B and A XOR B. I want you guys to try out the next two examples because they are pretty straightforward and they'll give you a good hands-on experience on how to build a decision tree. Okay, so if you see that, that was pretty simple. A second question, question 2, is on D tree learning or decision tree learning, where we are given a data set with 4 attributes, and the class is in the rightmost column, that is the home world, right? So if you see, there are 4 attributes that are species, rebel, age, ability, and the class. Basically, this is the class Y, home world, right? These are the features, and it consists of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points or 12 instances, right? Now, let's see how we can build a decision tree out of this. So, right, if you have this data set, the first thing to do, okay, I'll remove this part, and we'll just use the data set that is given, and I'll just write down directly what we have. Okay, so let's take species. Okay, so if you take species, there are 12 samples or 12 instances, out of which 5 gives positive and 7 give negative, right? In species are of 1, 2, 3, 4, 5, 6 type, that is pearl, bismuth, garnet, amethyst, and diamond, and jasper, right? So if you take these 12 6 items in a single attribute species, and you see the class distribution, right? For pearl occurs 3 times, out of which 1 is positive, 2 is negative, right? How do you see that? See, if you have this and you go with pearl, right? You have pearl here. So pearl 1, 2, and 3. It is occurring 3 times in species. Now compare your class, that is the home word, with the attribute that you want to split on. Let's say you're considering pearl, and pearl, right? So first pearl coincides with no, second pearl coincides with no, and the third pearl coincides with yes, right? So therefore, the distribution for pearl is 1 positive, 2 negative. Similarly, if you take bismuth, bismuth occurs once, just once, and that too with no. So the distribution for bismuth becomes 0, 1 negative. Similarly, if you take garnet, it occurs twice, amethyst, it occurs thrice, diamond occurs twice, and jasper occurs once, right? So using these, you can very well calculate the gain, right? Calculate the entropy from this, and then calculate the gain using all these attributes, okay? And similarly, you can go with rebel, right? Again, 5 positive, 7 negative. Entropy would remain same for all the attributes. So rebel is of just 2 type, yes and no, where yes occurs with and no occurs with 7 times. What this means is, if you have a tree learning, okay, and you take rebel, right? So yes occurs 1, 2, 3, 4, 5, but each time it is coinciding with the no in the class. Why, that we need to predict, right? And similarly, no 1, 2, and 5 times here, all coinciding with yes and twice with no. So that is why you write 5 times positive, twice negative. So this is how you distribute up your data set depending on the values and this attributes that are given. Okay, now let's say in the example that we have, in the example that we have for the species, we have a gain which is already given. You can calculate it as well. It would be a good practice to do it, because you have the answers in front of you, and like you can calculate the gain. And split info is given as 2.46. Similarly, for rebel, gain is 0.48, while split information is equals to 0.98, right? We have this information. Now we want to find out which attribute would the decision tree learning select as the split when using gain ratio, right? So what does gain ratio? Gain ratio corrects for a bias in information gain that favors attribute with many values, okay, by dividing it by the split information, right? So if you want to find the gain ratio for this, it would be 0.52 upon 2.46. Similarly, gain ratio for rebel would be 0.48 upon 0.98. So if you calculate it, gain ratio for species comes out to be 0.21, and for rebel it comes out to be 0.49. So as you see, the gain ratio for rebel, we should write gain ratio for rebel is greater than gain ratio for species. Therefore, we choose rebel as our splitting attribute, right? So now that brings us to our third question. Third question is basically you have three attributes A, B, C and a classifying class Y, and it is asking you what would be the training set error of this data set, right? And they want an answer in the number of examples out of 12 that would be misclassified, right? So you see these are 12 samples, right? Now if you look closely, there are repeated samples as well, right? Like for 001, but the associated class of 001 remains 0, right? 001, 0. Similarly, if you keep continuing forward, you would find 011 where the classifying class is 0 and 011 here where the classifying class is 1. So you see that for these samples, if this classifier encounters another data sample with 011, it would be confused so as to which class should it classify it. Should it classify it as 0 or should it classify it as 1? Right. Similarly, so that makes a number first error in our classification. That is when we encounter anything with 011, we will encounter a misclassification problem. Now continuing down the table, you see 110, 1, 110, 1. But in the last two samples, that is 111, you get two different classes, 0 and 1. Right? So therefore, for two values, that is 011 and 111, the classifier or the decision tree will have a misclassification problem. So now that brings us to our question 4. Okay. So question 4 basically wants you to explore what would be the maximum error for a decision tree. Okay, if um, it is to be learned on an arbitrary set of data where each instance has a discrete class value in one of k greater than 2 classes. That means we have multi-class classification, we have k greater than 2, and we can have an instance, each instance has a discrete class value. Okay, so what is the maximum training set error expressed as a fraction? Okay, so let's take an example where all the k class values are uniformly distributed. Uniformly distributed, right? So that means if it is uniformly distributed for each class, there are 1 by k samples, right? So if we have 1 by k samples for each class in training set, and let's say in the worst case scenario, in the worst case possible, our decision tree is only able to classify one class correctly, right? Or it is able to generalize or classify the data sample into one class only, right? So this would get just 1 by k samples correctly classified, right? True. If these many are correctly classified, how many of them are incorrectly classified? So k minus 1 by k, right? Total, if you take as 1 minus 1 by k, which results in k minus 1 by k. These are the number of samples that are misclassified, right? If these are the mistakes or these are the fraction of the training set that are misclassified, so the error would result in, so this results in a misclassification error. Now if any of the class has more than 1 by k samples, so that means those are the that is the dominating class. So the worst case would be our decision tree always predicts that class, but the error won't remain the same as k minus 1 by k. It would be a little different. So that brings us to our last topic of model trees. Model trees, we tackle a question in the PDF that we have. So model trees is basically it uses smoothing function where p dash or prediction is np plus kq upon n plus k, where n is the number of samples that you're using, p is the original prediction, the leaf node prediction, right? K is the target function that well approximates the value, or let's say k would be equal to true value of the function. Q, q is equals to the internal node value, right? And n is the number of samples that are there, and k is the true value again, right? So the question that we have, in this, the true value is given by y is equals to 2x plus 1, because this linear function or univariate target function well approximates the value of our function. So this gives us is equals to 5. This is the value of k. Now our leaf node will give us p as 5x plus 1, which is equals to 11, and similarly the internal node value would be 1.5x plus 1, that is equals to 4. Now we have p, q, k and n as equals to 2. Using the smoothing formula, we get n as 2, p as 11 plus k is 5, that is the true value, into internal node value is 4 upon 2 plus 5. This gives us 22 plus 20 divided by 7. This is equals to 6. This becomes your smooth value. So our smooth value, that is p dash, was given as 6. Our p initial was given as 5, and whereas our p was given as 11, because this was calculated by our leaf node, right? And the actual prediction, the true prediction k, was given as 5. Now as you can clearly see that the smooth value p dash is more closer to k than our leaf value that initially predicted it, right? So smoothing has improved the estimation of our model trees, hence smoothing is applied. So that pretty much covers up all the concepts that are required for decision trees and how to build a good decision tree and how to select the right attribute for splitting. I want you guys to go practice, and if you have any doubts, let me know. Thank you. See you next week.